Hello everyone. The title of this video is Identify Basic Toolkit Functions. Alright, so in this video I'm not going to be doing any particular examples from this free online textbook. It's at openstacks.org and I'm in their Algebra and Trigonometry text, section 3.1, called Functions and Function Notation. I'm under the heading Identifying Basic Toolkit Functions. I've also seen this referred to as a library of functions. And what these are, it's just basic functions that you're expected to know throughout a college algebra or pre-calculus or beyond course. And this is really just a starting list of functions you should be aware of and know what they look like on the xy plane without having to think too much about them. You should be really familiar with these. And this is just, like I said, this is just a starting list. So you got, the constant function, identity function, absolute value function, basic quadratic function or the square function, the cubic function, reciprocal, reciprocal squared, square root, and cube root. All right, and I'll go over how I would, now you can just kind of fly through these and look at how they look, and I'm going to show you on Desmos, on paper. Right? I'll probably spend more time than I should going over these, but I want you to get really familiar with these because they're going to come up a lot in videos beyond this video related to this particular book. But like I said, this is just a starting list. Later in the text, we'll see your basic exponential functions, your basic logarithmic functions, and if you go on into a trigonometry course, or sometimes it's brought up in pre-calculus, you'll see your basic trigonometric functions: sine, cosine, tangent, cosecant, secant, cotangent, and the inverse trigonometric functions, the basic versions of those. Then you might even get into hyperbolic functions, hyperbolic sine, hyperbolic cosine. So just please understand that this list of functions here, this toolkit, is really just the beginning, right, of the basic functions you'll be learning about throughout your mathematical career if you continue on with it. Okay. All right, so let's start with, as you already saw, again, you can just go through that table. I'm just going to kind of make each function separately on a separate piece of paper. All right, so again, basic toolkit functions, sometimes referred to as a library of functions, right? You're adding to the library in your mind, a collection. All right, so the first one I want to talk about is the constant function. So the general version of this is f of x or y or g of x or whatever you want to call it in function notation here equals, and then just c, where c is a real number, and it is a constant. It is not a variable. All right, yes, it's a letter right now, but it is a fixed number, where c is a real number constant. All right. And the graphs of these functions, y equals c, f of x equals c, y equals 2, 3, just horizontal lines. So I'm going to make a rough sketch here, and then I'm going to go to that Desmos website and show you a much cleaner looking version. Right. So here's the horizontal. The way I've set it up. Right. The input is x, the output is f of x, right, which is also c. Right. Both sides are equivalent, so they both represent the output. and this right side is how to calculate it. So you have x-axis, y-axis, or f-axis, since I called the function f. Now again, the table is very simple. If you were to make a table for input x, output y, or output f of x, it's no matter what you plug in for x, plug in 0. The output will be whatever c is. All right, no matter what you plug in for x, the output is c. So 0c, 1c, 2c, -1c, -2c. So you go to c, whatever value you decide c is. You go to c on the vertical axis, and then, like I said, no matter what you plug in for x, 0, 1, 2, -1, -2, 2.5, 1.2, pi, whatever. The output will be c, so there's 0c, 1c, 2c, -1c, -2c. And all these points here fall on a line, and it is a line that is horizontal. Right? It's something that's parallel to the x-axis, or the x-axis itself if c is 0. But yeah, it's a horizontal line. That's the graph of these constant functions. Okay. Yeah. So just to show you some basic examples. Again, this is a free online graphing calculator at desmos.com. Yeah, so I can just go, f of x equals c, and if you add a slider for c, see when c is 1, you get this purple line here. Let me make a different color. Make it red or something. Yeah, maybe you can see that better. And then you see this is f of x equals 1. Right? So you see at 1 on the vertical axis, you got every single point has a y coordinate of 1. And if I just move this around, it just moves the line up and down. There's f of x equals 3. All right, but no matter what c is, this is a horizontal line. All right. Okay, very, very simple. Yeah, so that's your constant functions. All right, the next in this toolkit, the list of this library of functions, the identity function. All right, so this is where you have f of x or y equals x again. So the reason it's called the identity function is my input is exactly the same value as the output. Input and output are the same. They have the same identity, I guess you could say. Right? So running an input through the function doesn't change the value's identity. I don't know exactly why it's called that, but that sounds good, doesn't it? All right. So again, here, very, very simple graph to make. I'll just make a rough sketch here, x and f, or x and y. And if I'm making a table, f of x or xy, input, output, right, it's very simple. Right? Whatever the input is, that's also the output. So 0, 0, input 1, output 1, input 2, output 2, input -1, output -1, input -2, output -2. So I'll just mark some notches here, some integers on the axes. And plot some points. Again, input 0, output 0, so the origin is on this, right? Input 1, output 1, input 2, output 2, -1, -1, -2, -2, 3, 3, 0.2, 0.2, pi, pi, right? No matter what the input is, the output, is the same value, y equals x. And it's just a line, right? You see all these points I plotted fall in a nice straight line. And this is a line, right, with a slope of 1. You might remember the concept of slope. It's a line with a slope of 1 and a y-intercept of 0. Right? That's it. Very, very simple. And there's no move in this, right? I'm not changing. Whatever my input is, that's the output. This is this line. This is the only identity function. Right? There were lots of constant functions when I changed the value of the constant. Right? I could make it whatever I wanted and get any horizontal line, but this is the only identity function. Right, so going back here, let's get rid of that. F of x equals x. See, that's it. Can't change that at all. And moving some points around, right, there's 0, 0, 1, 1. You see, no matter where I'm at, the x coordinate and y coordinate input and output are the same. Right, 2.2, 2.2, negative 2.86, negative 2.86, whatever. All right. Again, pretty simple in my opinion to graph that one. And the reason we're learning these also is later in this chapter, chapter 3 of this text, we're going to talk about transformations of functions. And we're going to see that, if you know these basic toolkit functions, you can transform them to make other functions pretty easily. So what we're going to see is that every line, right, every linear function is some transformation of the identity function. Right? We're going to see that later. All right. Next in the list, the most basic absolute value function. So it's just f of x, and just the name of the function says it all, right? The input is x, the output is the absolute value of x. Now hopefully you'll recall what absolute value does, right? It just makes things non-negative. The absolute value of a positive number is itself. The absolute value of a negative number becomes positive, right? It's the opposite of itself. And the absolute value of 0 is 0. Right? Okay, so again, I feel, and this with most graphs, these are usually pretty easy to draw a rough sketch of. X, y, or x and f, right? Whatever the name of the function is, that's the output. And I'll make a table. Right, with some points, x, f of x, or x, y. So input 0, right? The absolute value of 0, as I mentioned, is 0. Absolute value of 1 is 1. Absolute value of 2 is 2, right? The absolute value of negative 1 is positive 1. The absolute value of negative 2 is positive 2. Alright, so again, I'm going to go mark off some notches here for some integers on the x-axis. And notice I'm only going up on the y-axis. So yeah. Input 0, output 0. Input 1, output 1. Input 2, output 2. Input 3, output 3. Right? The absolute value of 3 is 3. Input negative 1, output positive 1. Absolute value of negative 2 is positive 2. Absolute value of negative 3 is positive 3. Right? And what you're going to see are these rays that form this V shape. Looks like a V. And what you're going to see in a later section of this chapter is that the absolute value of a linear expression, right, with x to the first power will always have some sort of V shape. Right, so like a V shape here. And for the absolute value of x, right, this ray on the right side has a slope of 1. This ray on the left side, this part of a line, has a slope of -1. So these are actually perpendicular. These are perpendicular. I put a little 90-degree symbol here. Now that's not going to be the case when we transform this. All right, like I said earlier, in a later section in this chapter, we're going to take this basic absolute value function and perform some transformations. Move this stuff around a bit. So in that case, they might not be perpendicular. But in this case, for just the absolute value of x being the output, they are perpendicular. All right, and this is it. This is the basic absolute value function. And let me go back here and do that. Right, so ABS of x. Right, ABS is short for absolute value in the Desmos here. And you can also actually put in the absolute value symbols if you want, but you have to go to the keyboard here, and they are located under the Functions tab, and I think Miscellaneous. No, Distance, Stats. Okay, well. Huh. Oh, it's right here. Open your eyes. Right, so there's the absolute value of A, it says there, right? Absolute value of X. Okay, excellent. Okay, so yeah, there it is. See and look, right? All these over here are basically, the same input is the same as the output, like the identity function. But over here, when I get negative inputs, right, we get the opposite output. Right, negative 2.28, positive 2.28, negative 3.38, positive 3.38, and so on. Right? Absolute value makes everything non-negative. Wonderful. Right, and they look, at first glance here, looking at this picture, they look perpendicular, don't they? Like these two rays. Okay. All right. Next one on the list is the most basic quadratic function, right, where you're going to have x squared as the highest power, and it's a polynomial function. I'm just calling it the square function because that's what you're doing to the input. Right? It's f of x or y equals, and then you take your input x and square it. Right? X squared. And that's it. Right? And again, this is the most basic version of a quadratic function. And later, when we get into transformations, in a later video, you're going to see that every quadratic function is just some transformation of this one, this basic toolkit function here. So once again, just a rough sketch by hand, and x and f or x and y. Make a little table. So the 0 input, remember the output's just the input squared, right? 0 to the second power, 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. And so on. Now you can put in, again, you don't have to put in integers. You can put in fractions. You can put in whatever you want. Right? Put in the square root of 2, you'd get 2 as an output and stuff like that. But integers are just easier to visualize, in my opinion. -1 times -1 is +1. Remember, a negative number squared is positive again. -2 squared would be 4. -3 squared would be 9. Right? So I'm going to plot, several of these points. Right, so here's some integers on the x-axis. And some integers on the y-axis, or the f-axis, just the ones that matter. 1, 2, 3, 4, 5, 6, 7, 8, 9 there. So yeah, input 0, 0 squared is 0. 1 squared is 1. 2 squared is 4, right? 2, 4. 3 squared is 9. Then you'd have 4, 16, 5, 25, and so on. Negative 1 squared is positive 1. Negative 2 squared, positive 4. Negative 3 squared, positive 9. Right? And these are not forming rays. These are not straight like the absolute value function. It's more curvy. Right? And all that I would ask is that you don't make the bottom pointy. Right? It's more rounded like this. And we get a shape that's called a parabola. Right? The graphs of these quadratic functions are called parabolas. Right? And once again, this is the most basic parabola. Right? Every other parabola is just going to be some sort of transformation of this parabola. And once again, let's look at a much cleaner looking picture on the Desmos site. So f of x equals x to the second power, and there you go, right? And here, so like 1.04 squared is rounded to, or is one, it actually would be 1.082. These all these are rounded to 2 3 decimal places. 1.93 squared rounds to 3.725, right? Because it should end in a 9 if you were squaring that, but 2.205 squared and so on, right? Go over here. There's negative 2.4, right? Somewhere. There it is, negative 2.4 that we had in our drawing, and so on. You just move the point around. You can see all the squares. You can also make tables for these things, if you want. Just click on the little cog here and you can add a table for the function. And then it plots points for the things that you put on the table. And I can put it whenever I want, right? I can put in the square root of 2 and get 2, right? And there's the point there. Right? Now you see again it's 1.414. That's a rounded square root of 2 to 3 decimal places. Right? Yeah, so you can make tables. It's very nice. I really like this site. Okay. All right, so that's your basic square function, basic quadratic. Next on the list, the most basic cubic function, or the cube function. And you do exactly what it says, right? Take, f of x or g of x or whatever you want, or y. And what you're doing is, the output, how you calculate it, you just take the input and cube it. Right? X to the third power, raise it to the third power, cube. Right? All right, and the same deal. I'm just going to plot several points, and hopefully we'll see a pattern and make a rough sketch. And then I'll just go to the Desmos site and make a better looking version of it. But here's xy, or x f of x. Now 0 cubed, right? 0 times 0 times 0 would be 0. 1 cubed would be 1. 2 cubed would be 8, right? 2 times 2 times 2. 3 cubed would be 27. Right? So I'm probably not going to plot that. Right? Then let's go to the negatives. Now negative 1 times negative 1 times negative 1 would be negative again, right? Negative numbers to an odd power, right? 3 is odd. Would be negative, so this is negative 1. And negative 2 to the third power would be negative 8. And negative 3 to the third power would be negative 27. And once again, you can also plug in decimals, fractions, whatever you want, irrational numbers. Okay, and then plotting some points. And maybe I'll make these a little tinier. 1, 2, 3. 1, 2, 3. And 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I probably won't go up to 27. Okay. Negative 1. Down to negative 8 here. Yeah, I'm not going to go up to 27 with these notches. But yeah, 0 cubed is 0. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. It's way up there. And it gets large very quickly. Negative 1 cubed is negative 1. Negative 2 cubed is negative 8. And again, it gets small very quickly as well. Big negative numbers, right? Negative 3 cubed is negative 27. Negative 4 cubed is negative 64. Now this will be pretty thin the way I'm drawing it, but it's just this kind of curve here. There's a cubic curve. Right. Don't know if it really has any special name other than a cubic curve. You know, like quadratic curves are parabolas. I'll just call it a cubic curve. Let's look at a much cleaner looking version. Right, so let's just change this square to a cube. And there's your. Now again, you zoom out, it's going to look real thin. You zoom in, it'll look a little more curvy. Right. And again, just move some points around, and you get input is whatever, and the output is the input to the third power. Rounded to 3 decimal places. Right. Cool. All right. And again, just every other cubic polynomial function is going to be some transformation of this one in some way. Every one that we're going to see anyway in a future video. Okay. Next. Again, the names of these functions are just describing what you're doing to the input. Right? You have the reciprocal function. So that's f of x or y equals, and you take your input x, take the reciprocal, right? This is x over 1. The reciprocal would be 1 over x, right? You just flip it over. Now, I hope it's obvious here that x cannot be 0. 0 does not have a reciprocal, right? 1 divided by 0 is undefined. But it can be any other value. Any other real number has a reciprocal. Okay. So what we're going to see, is that this graph's going to have a couple lines called asymptotes. The x-axis and the y. I'll call it the y-axis now. F-axis. I'll put little dots on them, little dashes. We're going to see the y-axis is what they call a vertical asymptote for this graph. All right, we're going to see the graph will get really close to it, but never actually hit it, right? Because the y-axis is the line x equals 0, and we saw earlier x can't be 0 here. Right? So there aren't going to be any points of the graph on the y-axis, but the graph will get as close to the y-axis as you want without actually touching it. And we're also going to see that the output will never be 0 either. Right? Here's y equals 0, right? The x-axis, and this is going to be a horizontal, what they would call a horizontal asymptote, right? It's a horizontal line that this graph will approach as well. And what we're going to see is that the graph will approach the x-axis also, but never actually touch it, because you plug in any number other than 0, this will never be 0. 1 divided by any number that's not 0 is never going to be 0. You're never going to have an output on the x-axis here. You're never going to have an output of 0. All right, so let's make a little table again. X, f of x. And again, you can't plug in 0, so let's not try that. The reciprocal of 1 is just 1. The reciprocal of 2 is 1/2. Right? The reciprocal of 3 is 1/3. And hopefully you see the larger I make x, the smaller the output will be. Let's keep with other positive numbers. Let's get closer to 0. How about a half, right? The reciprocal of a half is 2. Get even smaller. The reciprocal of a third is 3. The reciprocal of a fourth is 4. So you see, say here's 1, 2, 3, and then you got, a half, a third, and so on, a little tiny. Then here's, 1, 2, 3 on the y-axis, and then here's a half and a third on the y-axis, and you get these points. Again, the reciprocal of 1 is 1. Reciprocal of 2 is 1 half. Reciprocal of 3 is 1 third. And do you see how, starting from 1, 1, as I go to the right here, the graph, the outputs get smaller and smaller and smaller, but never actually become 0. They're always positive, right? 1 third, 1 fourth, 1 fifth, 1 sixth. They're always positive, just getting tinier and tinier and tinier. If I go out to a billion, the output will be 1 billionth. Very, very, very small, but still positive, right? So that's why I mean by horizontal asymptote. The graph will approach this horizontal line, but never actually become it. And then between 0 and 1 here for the x values, again, the reciprocal of a half is 2. Then get closer to 0. The reciprocal of a third is 3, even higher. The reciprocal of a fourth is 4. The reciprocal of a fifth is 5, right? The closer to 0 my x value gets, the larger the output. And again, x can't be 0 though, right? So I can get really, really close to 0 but never actually plug in 0. And if I get super close, if I plugged in a millionth, a billionth, right, the output would be a million. A billion, right, it would be huge. That's why I got the arrow here. Right? So this is getting, again, vertical asymptote of the y-axis. The graph is getting as close to the y-axis as I want it to be, right? I can plug in any value of x except for 0. I can get as close to 0 as I wish. And you see the graph there is getting close to the y-axis, but never actually becoming it. All right, now that was for positive inputs. You'll see the negative inputs are very similar. Right? So let me just instead of adding to this table here, if I plug in -1, the output will be -1. Right? The reciprocal of -1 is -1. The reciprocal of -2 is -1 half. The reciprocal of -3 is -1 third. The reciprocal of -1 half is -2. The reciprocal of -1 third is -3. The reciprocal of -1 fourth is -4, and so on. All right, so going over here, here's -1, -2, -3, and then on the y-axis, -1, -2, -3. And we'll go like here's -half on the x, here's -1 third. Sorry about the tightness of this. And here's -1 half on the y, -1 third on the y. Yikes, that's too tight. Alright, so yeah, reciprocal of -1 is -1. Reciprocal of -2 is -1 half, right? A little higher. The reciprocal of -3 is -1 third, a little higher still. And what you're seeing is, as I go to the left of -1, the outputs get higher and higher, but will always be negative, right? You get -1 fourth, -1 fifth, -1 sixth, -1 millionth, right? It's always negative still, but never actually 0. So again, a horizontal asymptote to the left as well. Graph approaches the x-axis but doesn't actually become it. Alright, then the reciprocal of -1 half, -2. Reciprocal of -1 third is -3. And what you're seeing again is, as I get closer to 0 on the left side, right, the negative side, the outputs get smaller and smaller. They go, more negative. So, -2, -3, -4, -5, -1 million, right? the closer to 0 I get on the left side, the bigger the negative output. Right? The graph will be, again, going down forever, never actually touching the y-axis, but getting as close to the y-axis as you want, right? A vertical asymptote. And there's your graph of the most basic reciprocal function, right? The most basic rational function. All right, so once again, let me put this in. Back on Desmos, 1 divided by x. And you're seeing this graph there, right? And again, you go to any point, right? The y-coordinate is just the reciprocal of the x-coordinate, rounded to 3 decimal places, right? So there's passed up 1, 1 here, right? 1, 1. Right? Here's, 2, 1/2 should be on this. Right? I just passed it up. There it is, 2.5, right? 2 comma 1/2, and so on, right? And the same thing goes for this left side. And you see how the graph, I mean, I know it looks like it's hitting the y-axis, but if you zoom in, it's not actually touching the y-axis. Same thing for the x-axis, right? You zoom out a bit, it looks like it's touching or on top of the x-axis, but if you zoom in close enough, you'll see it's not actually touching the x-axis. The outputs are positive all the time. Right? On this side, over here, the outputs are negative all the time, right? On this branch. Right, and this is actually another special kind of graph. This has a special name to it. It's called a hyperbola. Right, but it's a tilted hyperbola. You'd have to know about rotation of axes and whatnot to see how we can change this into a standard hyperbola. So I'm not going to really get into that right now. Just know what it looks like, this basic reciprocal function. Excellent. All right, the next on the list, the reciprocal squared. All right, so again, just the name of the function tells you what you're doing to the input. Right? We have f of x equals, now you take x, you take the reciprocal, 1 over x, and then square it, which would be just 1 over x squared. Because right? 1 squared is 1, so the numerator would still be 1. The denominator is now x squared. And just like with the reciprocal function, my input can't be 0. Right? So again, you're going to see the y-axis is a vertical asymptote. And also, the output will never be 0 either. Right? You got 1 divided by some non-zero number. That's never going to be 0. So you're going to see, again, the x-axis will be a horizontal asymptote, once again, for this particular function. Okay. Now, table. So yeah, again, you can't plug in 0, but 1, the reciprocal of 1 is 1, and that squared is also 1. Right? The reciprocal of 2 is a half, but when you square it, you get a fourth. The reciprocal of 3 is 1/3, but when you square that, you get 1/9. So you see, the larger I make x, the smaller the output gets again. Right? And the smaller I make x, right, if I make x tiny, like a half, the reciprocal of a half is 2, and 2 squared is 4. And then put in a third, right? The reciprocal of a third is 3, but then you square that, right? The reciprocal squared, you get 9. So you see, the smaller I make x, right? 1/4, I'd have 16, right? 4 squared. The smaller I make x, the larger the output gets. Right, so let's do that over here. There's 1, 2, 3. And then the y-axis, let's go up to 4 here. And, I'm plugging in a half and a third, and I'll just plug in a half. Alright, so yeah, the reciprocal of 1 squared is still 1. The reciprocal of 2 squared is a quarter. Right, so let's say that's about here. just eyeballing this stuff. All right. I'll go to the Desmos site for a much better picture. The reciprocal of 3 squared is 1/9, right? Very tiny. And again, you're seeing, well, when I plug in 4, I'd get 1/16th, and when I plug in 5, I'd get 1/25th, and it'll always be positive on this side. But it gets smaller and smaller and smaller, and the x-axis is going to be a horizontal asymptote. Right? The graph will never actually touch it. All right, then the reciprocal of a half squared is 4. Right, so this actually shoots up quite a bit. Right? You'd have 1/2 4, and then 1/3 9, and 1/4 16, and if I went to 1/10, just 1/10, 0.1, the output would be 100. Right, the graph, again, the y-axis, x can't be 0, so you won't have any points on the y-axis, but the y-axis will be, again, a vertical asymptote. Graph will approach it, but not actually become it. And then all this stuff, because this is a square, will be exactly the same on the other side with negative inputs. Right? When the reciprocal of -1 is -1, but then you square it, you get +1. The reciprocal of -2 is -1/2, but then when you square that, it's +1/4. So I'm just going to put all negative signs on all these, and we get all the points on the other side of the y-axis. So -1, -2, -3, -1/2. And yeah, -1 output, +1. -2 output, +1/4. -3 input, the output's +1/9. -1/2, the output +4. And you basically get just this curve from the right side kind of flipped over the y-axis, or reflected over the y-axis. Right, where it's shooting up really, really high, going to infinity as you approach 0, as your inputs approach 0 from the left. Right? And then as your inputs go this way, right, you plug in -4, you'd get 1/16th. Plug in -5, you'd get 1/25th, right? It's really, really tiny, but still positive. Almost, it's approaching the x-axis, but not actually touching it. There's your basic, reciprocal squared graph. And once again, let's go back here, and 1 divided by x squared, and there you go. Right. Now I know it looks like the x and y axis are being hit, but like I said, you zoom in far enough, you'll see that the axis is not actually touched. Right. Neither of them, the x-axis nor the y-axis, are touched here. And you go to any of these points, right? It's the x-coordinate, and then the y-coordinate is just the reciprocal of the x-coordinate squared, rounded to 3 decimal places. Right? So, and you can play around with this, make a table, whatever. Right? Cool. Just know the basic look. Right? That's all you're asked to do really for any of these, is know what they look like, so you can transform them later. Alright, let's got a couple more. Almost done. Right, we got some roots. Alright, the square root function. Now this is the principal square root, right? The non-negative one. So take f of x or y equals, and you just take your input x, and take the principal square root of x. So remember this. So this is never going to be negative. This is never going to be negative, right? This is asking for the principal square root. Remember, whenever you see this symbol, even root symbol, square root, fourth root, sixth root, whatever, it's asking you for the positive one. Because yes, I know every positive real number also has a negative square root, but that's not being asked for here. Right? And another thing, the x and y axis represent real numbers. So I would like my output, in order to make a graph, I would like my output to be real, not imaginary. So one condition on this is that x has to be non-negative. Right? X has to be a non-negative number. X has to be greater than or equal to 0. Because if you plug in a negative number, your output will be imaginary. Remember, the square roots of negative numbers are imaginary, not real, and I can't plot them on the normal XY Cartesian plane. Okay, so that'll help me make my table. Right. Start with 0, right? Start with 0. Now the square root of 0 is 0. If I plug in 1, right, the principal square root of 1 is 1. Now, I wouldn't plug in 2, If you did, the principal square root of 2, the non-negative square root of 2 is about 1.414 or something, right? It's not nice. So I would plug in, say, something that I know is a perfect square, like 4, right? Square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4, and so on. 4, not 14. I don't know why I wrote 14. And so on, right? So 0, and then, here's 1, 2, 3, 4, and then 5, 6, 7. Let's go out to 9, 8, 9. And outputs 1, 2, 3, right? So yeah, so again, input 0, output 0, input 1, output 1, right? Again, you could do input 2, output, 1.414-ish. That's not wrong. And then 3, whatever the square root of 3 is, which is about 1.7. And then 4, 2. Right? Then 5, square root of 5, 6, square root of 6, 7, square root of 7, 8, square root of 8, 9, 3. Right? 9, the square root of 9 is 3. Just kind of eyeballing this stuff here. And what you actually get is, half of a parabola. This is like half of a parabola that's opening to the right. Now, obviously, the other half would be the negative square roots, but we're only asked for the principal square roots, right? The non-negative square roots that when this symbol is shown. And that's it. Very simple. So I'm back here. So again, to put square root in your Desmos, you just put SQRT, SQRT, and then X, right? And notice again, right? See how the only values of X coordinates are 0 or greater, right? 0 or greater. And even when you go to make a table, right, you'll see when see for negative values it's saying undefined. It's because they're imaginary, right? Square roots of negatives are imaginary. But then you pop in 0, 1, you see 1.414-ish for square root of 2, and so on. And you can plug in whatever numbers you want into the table. Wonderful. So yeah, again, just like half a parabola, opening to the right. And again, just know the basic shape so that you can transform it later. And then finally, on this list of toolkit functions, this basic library of functions that will be added to later in the course, later in the text, the cube root. The cube root. So this is f of x or y or g of x or whatever you want. Right? Just take the input, and you're taking the cube root of the input, right? Cube root of x. Now this is the real cube root. No imaginary, and nothing with an imaginary number involved. It's technically, every real number. Every number has 3 complex cube roots. We're taking the real one, right? I want my output to be a real number. Yeah, and x can be any real number here, though, right? Remember, you can take cube roots, odd roots of anything, not like square roots, right? So, and this will be kind of like that cubic curve from earlier, just, going in the other, instead of going bottom to top, it's going to be going left to right. You'll see that when I make this graph. It's like the cubic curve earlier, but instead of going bottom to top, it's going left to right. You'll see. Right, so again, f of x And so, the cube root of 0 is 0. The cube root of 1 is 1. 1 cubed is 1. The cube root of 2, know, what, I don't know what that is. It's 1 point something. So yeah, so like I wouldn't plug in 2 or 3 or 4. I mean, they won't. You get an output. It's just not nice. I'd go out all the way to like 8. Right, the cube root of 8 is 2. Right, and the cube root of 27 is 3, and the cube root of 64 is 4. And then for the negatives, it's a little different, right? Cube root of negative 1 is negative 1. Right, negative 1 to the third power would be negative 1. Again, cube root of negative 2, I don't know. Right, cube root of negative 2 is not something nice. It's real though, right? That would be a real number. It's just not a nice one. It'd be negative 1 point something. So I'm going to go out to negative 8, right? The cube root of negative 8 is negative 2. The cube root of negative 27 would be negative 3. The cube root of negative 64 would be negative 4, and so on. Right? There are lots of points to plot here. So I'm just going to go out to 8. 3, 4, 5, 6, 7, 8 on the x-axis, and negative 8. There's negative 8. And then, just up to 2 on the y-axis and negative 2 on the y-axis. Okay. So yeah, cube root of 0 is 0. Cube root of 1 is 1. The cube root of 2 is 1 point something. I don't know exactly where it is. It's a little higher than 1. And then, cube root of 8 is 2. And the cube root of negative 1 is negative 1. The cube root of negative 2 is, negative 1 point something, a little lower, right? I don't know exactly what. The cube root of negative 8, though, is negative 2. And again, you're seeing something very similar to the cubic curve earlier in the video, but just going left to right instead of up and down. Right? So something like this. So this is going up forever, just very slowly. I'd have to go out to 27 to get an output of 3. I'd have to go out to 64 to get an output of 4. 125 to get an output of 5, right? It's going up forever, just very slowly. Right? Same thing this way, it's going down forever to the left, just very slowly, right? I'd have to go out to negative 27 to get an output of negative 3, and then negative 64 to get an output of negative 4, and so on. Right? Okay, and once again, show you on the Desmos site here. Now, unfortunately, I don't know how to type a shortcut for cube root, but that's where the keyboard comes in. Alright, so they got square root here. Let's go to some functions, miscellaneous. Here we go. There's the nth root. And I can enter the index of 3, right? So there's the cube root of x, and here we go, right? This short, this again, kind of like the cubic curve, but going left to right instead of up, down, instead of from bottom to top. And once again, you move the point around here. Every y coordinate will be just the cube root of the x coordinate, rounded to 3 decimal places. Right? And just to see some table stuff, right? Right, so yeah, the cube root of 2 I said was 1 point something, right? It's about 1.259921. This point here, right? They rounded to 2 decimal places here, 1.26, but. Yeah, so every input, the output's just the cube root of that, the real cube root. Great. Okay, and that's it. All right, that was a lot. I just want, and again, you can go back, to and look at the charts that they made and the pictures they made in the textbook. All right, they got the constant, identity, absolute value, quadratic, the square or quadratic, cubic, reciprocal squared, square root, and cube root. They have them all pictured here in this table. Get to knowing this table. Get to knowing what these basic toolkit functions look like. This basic library of functions. Because it's going to help you out immensely later in the chapter when we are doing transformations of these functions. I'm hoping that watching me go through these 9 toolkit functions, helps you get those in your head. Right? Helps you remember those pictures, what those basic functions look like. And like I said, I promise you, getting these down pat, understanding what they look like, knowing how to make them, will help you when you are doing transformations later. And thank you very much for watching.